Hi, today we will discuss forces of nature. In engineering, we are usually bothered with the gravity. The force due to gravity is the weight of the material. So in that case, it's the weight of the structural member. Aside from that, we have the humans, the pedestrians. Tanawagan ninyo, nga pang dive sila sa kilid sa tulay. Also, with the pool live load in the bridge. So with the hydrostatic forces due to water. The soil pressure, as you can see, ilang gibutang retaining wall diya sa Maloco. Naugno ra giya. Kini siya naugno tungod na siya sa soil pressure. Aside from that, strong wind. Winds can be simulated using computational fluid dynamics. Then after that, we use wind tunnel test to finalize the design. Also, we have the earthquake forces. Actually, uh, theoretically, the Earth is composed of tectonic plates. These tectonic plates are moving, are always moving. Siguro hinay lang siya, pero pag dako na yung pressure sa ilalom, mabuto na gina siya. Pag buto na niya, mulihok yun ang tectonic plate. Pag lihok na niya, tungkol sa kadako sa tectonic plate compare sa tua, the Earth will really move. So the movement is on the ground. It can be horizontal or vertical, but normally the largest force is due to horizontal movement. So kini siya, bali ni siya. Ang yuta gud may muliho. And then, just like kanang gasakay kay mo bus, nga tindog, then mukalit lang siyang brake, di ba? And the tendency is ipundog na to tong tail. Pero kay pagpundo na to sa tong tail, atong lawas mo mukuyog sa bus pag brake. So the same is true sa building. When the ground is shaking, the inertia, the mass or the weight of the building, dili siya ganahan mo kuyog. Since di siya ganahan mo kuyog, so magpabilin siya. Move ang ground, ang building magpabilin. So na siya movement. There will be displacements. The problem of that is that how do we apply it to the building? We make some assumptions to idealize it to idealize the concept. We look for an equivalent force. So that's why in earthquake loads we call it the static equivalent load, equivalent lateral force procedure. So there will be forces at the ground. We call it the shear force. That shear force will be transferred to the floor, different levels of the building. Aside from that, we have what we call what I call the terrorist act. The Twin Tower in New York collapsed in 2001 due to the jet plane. Yang gibangga ang building. Ituyo ka nagbangga. Kay duha man ni kabuk building yan lang giigo. Aside from that, the building collapsed due to explosion and fire. So these are the man-made forces. Then with that loads, if we have to apply these natural and man-made loads to the structure, there will be some load effects. Na siya reaction. If you apply the force, there will be an equivalent reaction. And what would be that reaction? It's about the structural effects or the load effects to the structure. It is in terms of, to simplify it, tension force. Tension means pull, birahon mo. The material will strengthen, lengthen, taas siya. Just like the tug of war, as you can see, the two person A and person B are pulling each other. So they are pulling a tension force. This is usually applied in structural engineering in terms of this one cable stayed uh, bridge, the Sonneberg bridge. Also with the Brooklyn Bridge, this is a suspension bridge, so it carries tension. And I want you to read the history of Brooklyn Bridge. It's really a nice story. Maybe na lang siya uh, maluoy pud ka anyway sa story, but at least they were able to construct the Brooklyn Bridge. Imagine the midspan is almost a kilometer, 486 meters in 1890. Aside from tension, we have the compression force. Tulod. We with compression, the member will shorten. Mugamay siya. Imo man siyang doon. They apply it in the Sagrada Familia building in Barcelona. It was done by Antoni Gaudi. He is the architect. So sorry, this is the the ceiling. I just love the ceiling of the Sagrada Familia. What he did is actually makita ninyo mura ba yapon siya kahoy na siya poste na siya sanga. Pagapot sa ibabaw may sanga na po siya. The concept of these columns is just like the hanging weight, this one. Siyempre, gihang man mo siya. This is intention and these are the loads. Since this is purely intention, pag balihon na nimo, ma-compression na siya. Okay ni, ibali siya. This is now in compression. Ayan. So, this shape of the hanging chain was used in designing the column of Sagrada de Familia. It's really beautiful actually. It was the idea is from Robert Hooke's hanging chain, which forms catenary in tension under its own weight. Pag balihon mo siya, it will stand in compression. So as you can see, if you visit the Sagrada Familia in Barcelona, sa Opus Manata, you will see the Gaudi's hanging weights. This is his model in designing this structure. He's quite clever, right? So he used the hanging chain concept. Then ibutangan niya dagang higot-higot aron maporma lang niya yung nani. And then the formation balihon rin siya mao na ang building. So here is the concept used by Poligny. Tension, then pagbalin niya, it is now compression. It becomes an arc. Di ba? So we have the tension structure and then the compression structure, which is an arc. It was also used in the design of the dome of St. Peter's in Rome or sana siya Vatican. Man siya. Aside from that, Heinz Eisler, or a structural engineer, a Swiss structural engineer, actually had this experience during winter. He observed that if you have a tinsel or clothing, ihang mo siya. Pagkaugma nanggahi na siya sa ice because during winter, tugnaw kayo manggahi na ma-ice siya. Then what he found out that pagbali niya na karon because this is purely intention. Pagbalian na niya, may man siyang compression. Just like this one, this is intention, hanging cloth, and then pagbali niya mo, may man siyang compression. So these are the things that Esler made. This is a shell, 3-point supports shell structure, which is purely in compression. The same is with the Italian engineer Nervi. He also used the same. Mura na siya kawa, balihon niyo mo, tangani mo siya og tubig. Siyempre, bira na siya tension. So, pag balianan niyo mo karon, it becomes compression. So, most of these are in compression. Except, of course, the portion kining gahawid sa mga supports because these are in tension. We call it the tension ring. So bisan pag dili na nimo ni siya ikalod, as long as you have the tension ring, this is quite stable. Kay kini na may manghawid ang tension ring, nakapalibot siya. Also, we have the Salgina Tubel Bridge, designed by Swiss civil engineer Robert Millard. This is an arc bridge, as you can see, na compression. So with the oldest cast iron bridge in England, designed by Thomas Telford, as you can see, this is made of cast iron. I mentioned last time that cast iron is good in compression but not in tension. That's why Thomas Telford designed this bridge to so that the cast iron will carry in compression. This is also used in the flying buttresses of the church in Europe. Habog mo mga church sa Europe pero niiwang siya. Kung kinilang wall dili mo magdala, di siya kadaog. So it has to transfer the force through compression on the other side. I-buttress. Kini, dako siya. Lapad. And by transferring that force, the compression force, then survive ang building. Taas man siya anang niwang. Kung wala na siya nga support sa kilid, maog no ang structure. Also, I mentioned last time, much better kung tension tanan. That's the efficient way of using the material if your material is good in tension. But if your material is good in compression, then it's better to make a structure na compression na po siya tanan. But there are structures also that is both in tension and compression. Hindi mo malikayan sa man-made structures. These two will always complement each other, the tension and compression forces. Just like this truss, this is a unique truss in Central Station, Berlin, the Berlin Hauptbahnhof. As you can see, the curve siya, the curved portion carries the compression, and then ang sa opposite midspan na in tension, and then sa gawas din niya, which is also in tension. As you can see, the computer modeling, makita niyo ang effect niya by applying the load. So that's why they were able to design it in that way. This is similar to the Waterloo Station. Mao gyapon, compression sa taas, tension sa ubos. In that way, you can always create large structures. Aside from that, we have the tensegrity. This is what I'm saying, the tension integrity. Tensegrity is short for tension integrity. The structure is actually stabilized by tension and compression. And as you can see, because tension is quite efficient, so gagmay ra ang imong material, gagmay siya og diameter compare sa struts which is in compression. So kung di kayo mo klaruhon, only struts ang imong makita, wala siya tendon or tension. Aside from that, we have the bending moment. Bending itong pick-on niya. You will bend the structural member. One of example is pole bolt. As you can see, tanaw, grabe ang pagka baho. But since the pole was actually designed to carry that load. Aside from that, the diving board. See, mubaw gyapon ang diving board. Okay, muambak-ambak man siya. Pag-ambak na dive. Also, the application is for buildings. I give you the dancing house. It's quite unique in Prague. Aside from that, we have the torsion. Torsion is mura katong galabaka. Imo siyang pugaon. Pugaon nimo ang building or structure. We have this turning torso designed by Santiago Calatrava. He's really a well-known architect in Spain. The turning torso with the inspiration from a human torso. Actually, the tower was designed to appear as if in a state of torsion. This is not in a state of torsion. Actually, it is not, but the appearance is a good example of what would happen theoretically if a turning force was applied to one end of the tower. The uniqueness of the human body is that our bones, our muscles can carry tension and compression, bending, but not good in torsion. No, it's not really good in torsion. So that's why this turning torso is not really intense torsion, but of course if there will be wind forces on this side, then pwede siyang lubagon niya. One of the most common examples with torsion is this bridge. Kini nga curve mo gid siya. So nagani siya torsion. This one. Di na niya mamalikayan. May torsion. Aside from torsion, we have shear. Shear, slice, di ba? Slice on niya. So ano, i-slide niya. Ang square nga cube, if you have shear, may mo siya nga diamond shape. Kaya mo sibog mo siya. Shear is usually applied in shear walls. So most of the buildings have shear walls, just like in the earthquake process. Siyempre, gikan man sa ubos ang force shear and we just distributed an equivalent lateral force sa kilid. Aside from that, we need to learn from failures, especially construction failures, so that when we design, we will be able to design efficiently and effectively by learning to our failures, from our failures. Here is a quite common, the Leaning Tower of Pisa. Nga naman siya, humok lang yuta sa Pika side. So nag-lend siya, minaog ang foundation. So what they did is they tried to correct this one. But they found out that it seems like daghan naman ninoy gusto mo tanaw. Maayo siya mong tourist destination. So what they did is that wala na nilagay straight yun siya. They left some leaning angle, and then they supported the bottom kaning nag-failure nga foundation, i-stabilize nila, and then mo na na siya. Likod kay na siya, di na siya basta nga matumba. But you can see it's still leaning. That's the effect na. And daghang kayo permentatorista diyan. Aside from that, we have this building, the topple down building. Sobra siya kanipis. Wala pa gani ang linog. Samot ang nailinog o hangin. Collapse siya. I think because of the foundation. Sobra kanipis ang foundation and it's not really stable enough. In your exercise, laboratory exercise, you will realize that if you have blocks and then sobra siya kanipis, taas sobra kanipis, pwede siya i-topple down. So you need to stabilize your structure in order that it will stay at place. This one, the Hyatt Regency in Kansas City, it collapsed. The fourth floor, I think, collapsed due to siyempre na party na kasayaw dito ni naganin og namatay. Live load lang plus impact, delikado. Also, we have the Tacoma Narrows Bridge. Bago rin siya na built in 1940s, but due to constant wind, there is sa Sapagagi, hinirang hangin, mga around 60 miles per hour. That's, I think, mga 90 to 100 kilometers per hour. Hinirang ganun siya sa tinod lang, di ba? Dili pa na bagyo. But due to constant mapaghapag sa hangin, and I think because of the aerodynamic design, dili siya maayo pagka-design in aerodynamics. So, nahinay siya o twist na hantod sa nag-oscillate na nun siya hantod sa naog. No? Also, we have the Arc Bridge in Taiwan. It was collapsed recently. Fortunately, isa ra to katrak ang dapas nga makatabo. And I think wala man siguro namatay. There are only other people nga naigo diri sa ubos. Moray problema. Ambot nga ano kung di mo sila alam sa tulay na park sila bangka naigo na noon. This is purely in compression, the arc. And I think it collapsed due to the tendon. I don't know kung kawa kita sa official report, but initially sa video ani murag naputol ang isa cable din nagsunod na din siya. Here is the Titanic departing from Southampton on April 1912. And sailed towards the USA. And along the way, because it's winter, na mga ice, naigo ang tukod matukang Jack o Gross na kuan din noon bitaw naigo ang iceberg ang ilalom. This is one of the problem of structural steel. Pag medyo bugnaw na kayo ang area, the steel becomes brittle. Ductile mong ang steel, pero due to very low temperature, the steel becomes brittle. So manang dali na kayo siya na daot. This one, the hotel in Baguio City in 1991, the Luzon earthquake, wala pa matawa ni, the very large magnitude Luzon earthquake hit the Luzon. In Nueva Ecija ata ang epicenter. Imagine, the epicenter is in Nueva Ecija, but the heavily affected area is Baguio City. Layo na kaya sa Nueva Ecija. Tanawan niyo sa mapa, Nueva Ecija to Baguio City. Mura siya na imong pankay. So this is the effect of a strong magnitude earthquake. And also we have the Twin Tower, due to nabanggan siya gibangga siya sa eroplano, then explosion and then fire, nahugnog siya. And that's the effects of the forces on our structure. If we can only design our structure strong enough to handle these forces, then our structure will survive. But unfortunately, most of our structures has a time frame. Normally, ang mga buildings is around 50 years. After more than 50 years, bonus na siya. But usually, it should be designed up to 50 years. But if we can design structures up to 120, 200, or 500, or 1,000 years, why not? We will be solving our sustainability problem with the materials as long as the structure will last longer, then it's good for the environment. But that's the direct effect of having new technologies. The high strength materials usually results to smaller sections, 6-year structures, but normally it will not really last. Unlike the old structures na halos compression siya, baga maputay nga wall. So kung wala lay earthquake, dili po siya man siya. So it will last 2,000 years, 3,000 years, 4,000 years. I believe if we can only design a structure, something like that with the new technologies, then it would be better for us. Thank you.